Okay, hello everybody, welcome back. So today we're going to talk about endgames, one endgame in particular called the Cauchy endgame. And so today is all about what happens at the end of a homotopy where we can't avoid multiple roots at the end. Okay. So I want the easiest example possible of a polynomial with a multiple root. X squared, awesome. As usual, we'll have this start system, which I've been calling the Bezier start system. It's also called the total degree start system. In fact, right now, the only thing that makes sense to call this is the total degree, because I haven't told you what Bezier's theorem is. Okay, but later we'll see it's the same thing. Okay, so we're not going to use any gamma trick here, just as an illustration. And I want to give you all a moment to try to work out the following steps. So just for your own check that you're following everything in the course correctly, I'm just going to put down some steps. We'll work through it. And yeah. So first of all, write down the homotopy that we've been writing here. And go ahead and expand it and simplify. There's only one t-value, namely t equals 0, that actually gives a system with a multiple root. You'll have two homotopy paths. And I feel fairly confident that you can actually write down formula for each of the homotopy paths. For t in this unit. And finally, I want you to try to extend these functions to functions on C. Okay, and that's where our problems will begin. And that's where the discussion will start. So I'm going to go ahead and pause the recording and continue it after we've all had some time to think about it. If you're watching on YouTube, feel free to pause the YouTube video now. Okay, welcome back. Does anybody want to give me an expression for this homotopy? Yeah, right.
X squared minus t.
Yes, thank you. So this is h of x t is x squared minus t. Okay, so for any particular t value, you will have two solutions. And how would you, let's skip to here for now. How would you describe those two solutions? As t goes from 0 to 1, what might you call the solution to x squared minus t? A square root of t.
Yeah. Right?
And so you have two of them.
Yes.
Right? So of course we usually mean the positive square root when we take when we write the square root sign of a positive thing, and then we'll also write the negative square root. And indeed, that's what this homotopy looks like. This is t. This is negative root t. Good. Awesome. How would you show that t equals 0 is the only t value which gives a multiple root.
Take the polynomial as a function x and then differentiate it. And then show
Yeah, let's
that
take the derivative with respect to x, we get 2x. And that means x has to be 0.
and that can only happen at
T equals 0.
yes.
Perfect. Good. Right, you have a multiple root when your polynomial system and its derivative both vanish. You just follow your nose, write that down, pretend t is a parameter or a constant, and conclude that x and t both have to be 0. Okay, raise your hand if you've taken a complex analysis class before. All right. Hand raising online is harder. Can you extend these functions to functions over C? Let's try. Yeah. Okay, so if I'm writing complex numbers, like say with some modulus and some angle in the complex plane, and I want its square root, I might be very tempted to write this. Because indeed, when I multiply two complex numbers, the moduli multiply, the angles add. So root r times root r is r. Again, this is non-negative, so this makes sense as a function over positive non-negative reals. And then yeah, I'll just add theta over 2 to theta over 2 and get theta. Boom, I think I've done it. Right? Any complaints?
Yes. Yeah.
Yes, complaints? Okay, what's the complaint?
What about the pi?
But so I
Okay,
started
fine.
away to.
Pi lives in the theta. Sorry?
I mean, so theta can change by 2 pi, so theta by 2 might be changing by pi.
Yeah. I might even be tempted to write something like this. Okay. Okay. So now let's try to think of whether or not that is like well defined over the whole complex. Like, so functions with a particular input have to have like one output. Right. So let's think about this. I want to think about let's shove t equals 1 here, so I don't have to draw such a big loop. I'm going to think about the unit circle in the complex plane with coordinates t. I'll start up here, so that t equals 1. And I think I can at least locally extend this here. We're going to see if whether or not this is a global extension of this function. Okay. Okay, so here I am 1 e to the 0. Right, angle is 0. Great. But as soon as I go to, let's say, 45 degrees, pi over 2, or pi over 4, then what is happening upstairs is, let's just have a picture here. So here's when t equals 1. And here is when t equals pi over 2. So t wants to be 90 degrees, but then we have it. Right? So that's what happens when we're right here. Okay. And indeed, as I scroll around this at some rate, my solution is scrolling around at half that. Okay. Which means, what happens when I go all the way around? I have moved so if this is going to define some continuous function from Ct to Cx, well, it now looks like it has 2 values. Okay, that's a problem. Functions don't do that. Okay. Yeah, so if you love your complex analysis, you can also kind of think of this as like 1/2 log z, and you need a branch cut of the log. This is the problem. Okay. And if we tried that for this expression here, again, like locally we're fine. Locally we can extend continuous. But we actually already knew that because that's what analytic continuation is. Right? So we're applying implicit function theorem everywhere, and we can locally move around. The problem here is a global statement. So if we tried it here, we would go there, like that. In fact, if we performed analytic continuation over this point around the circle, we would have to go around twice to get back to where we started. Does that picture make sense? Is there a K pi missing? Is there a K pi missing?
Yeah, I mean, usually we say theta plus 2k pi, so.
So I could do that. I could do that if I'd like. Yeah. Yeah, I don't need my 2k pi. I just need my K pi, but I'm happy just having two different expressions and saying that there's a problem. Okay. Okay, so this last observation shows that you can't extend these functions to C. And so this is not well defined as square root. Okay. And we know that we can commute the solution x equals 1 as we go around the unit circle once to x equals -1. That is not a problem, that's actually a feature. So that phenomenon is called monotomy. Okay. So you have to go around twice downstairs until you came back to where you started. Yeah. Great, and so we'll get back to this monodromy story in a little bit. So for now, I want to think a little bit more about this this circular boundary that has twisted kind of twice up here. So one thing I can do is I can think about looking at a new parameter, getting a new complex plane. So that essentially one wrap around this circle really does take me all the way around. Okay. So I can map this. This is just an S squared. So S with S squared. If I go around S from 0 to 2 pi, I've gone around here twice. Great. But more importantly, we have these solution paths upstairs. They form an algebraic variety that has x coordinates and t coordinates upstairs. Just think that out by x squared minus sideways square. And near this problem point here, we can look at the preimage and we can actually parameterize it by a disk. Okay, so we're going to take a really small disk here, look at its preimage. Okay, so there are no path crossings or anything, so this is all nice and smooth. And it actually is a copy of a punctured disk. In fact, this map is the identity in the first floor. So let me just convince you that that really is what things look like near t equals 0. But what I have to do, I would have to convince myself, let's call this map big P. This will be little p, this will be my var p. Okay, I have to convince myself that my phi of s, var phi of s really is identically same. All right, let's plug it in. X becomes just s, t becomes s. So what I've done is I've parameterized what's going on. And you can see that really explicitly. Okay. And this is a nice function. This is just the identity. Here. Now, in general, it's not going to be as nice as the identity, but it is going to be a so-called holomorphic function, meaning it's complex differentiable, meaning there's a power series locally expressing that function. And that's going to allow us to actually understand this target value by fully understanding the values on the boundary. Okay, so taking complex analysis, this is some contour integral. We're going to use the Cauchy integral formula to evaluate the value of these paths at t equals 0 without ever having to get anywhere close to t equals 0. Okay. So far, so good. And throughout, I guess I should be referring to the system. And the observation here. There exists this map from the function, so a disk. So all the radius epsilon around 0 minus the origin, so some punctured little disk here. To x, which locally parameterizes this. It's holomorphic. Explain why this exists in a little bit. And if I then project, I get some power map, S to a power. In this case, this W is 2. So, Cauchy integral formula. We have a holomorphic function on some open set U inside C. And containing disk the epsilon stuff not of radius epsilon not of C, the circle counterclockwise oriented around the boundary of that disk. Then I can evaluate this function at some A, for A inside anywhere inside the disk, interior of the disk, as contour integral around C of phi z over z A dz. This is the Cauchy integral formula, but this is not a complex analysis class. I'm not interested in you understanding everything about this at all. You don't even have to know what a holomorphic function is. You just have to believe me when I say certain ones exist. Okay. But if you're into complex analysis, this is going to be fun. What this is saying. Okay, so first of all, if I integrate just the function 1 around this circle, I get 2 pi I, by the way. And so you should think about this as saying that the function value at A is the average value around the boundary. Okay. And actually, let's unpack it for when E is the identity map, and A is 0. Okay, because that's the situation we're in over here. We're going to be applying this theorem to the same notation as this. on that. Let's do it. Okay, so there's some x star here. It's a multiple root. I don't want to get close because Newton's method is awful. This analytic continuation gives me like this z-nose, a paradox where I only get half and half closer every time. Takes a long time on a computer, doesn't converge quick, blah, 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 blah. This stuff, yeah, okay. So what are we gonna do? We're gonna try to stay away at some epsilon. Okay. Great, in this case, we take epsilon to be 1. All right. So b of 0, so a will be 0, b will be b. Okay, our epsilon will be 1. When do you get to do that? And our z naught will be 0. Yeah.
Sorry, could you just clarify what the map pi is here?
Yes, very good. Thank you. So up here we live in coordinates x and t, and so any point up here of the form x star t star, we'll just get mapped to t star.
So projecting.
Yes, thank you. Yeah, so this is the natural projection onto the second coordinate. And this has kind of been implicitly in the background the whole time. So in this case, we have this 2-to-1 map, except here, it's not 2-to-1. So only finitely many points in which you don't get a 2-to-1 map. And we kind of identify solutions to the polynomial system at this t value with the phi of this. Right, because of course the solutions are actually x values here, but I'm drawing them as like xt pairs here. Right? Great, good question. This is actually the main character of the whole course. Okay, so that's a great question. We should really love. All right, so let's so this phi of 0, by the way, is x star. That's what we want. And Cauchy's integral formula says this is t pi I integral around you know, the boundary of this unit disk, so b1 0. And what do we have to do? Well, we take p of z. Okay, well that's just z. Okay. And we do okay, well, we'll follow our nose and we'll see where I'm in that state. Okay, we're going to parameterize this boundary by, say, theta. Yeah, theta goes to e to the k. Right, and then theta is going to go from 0 to 2 pi. So this becomes the integral, sorry, 1 over 2 pi I, the integral from 0 to 2 pi of e to the I theta, e to the I theta, e to the I theta, e theta, because I've applied the chain rule on the data. Great. 1 over 2 pi I, integral from 0 to 2 pi. I is just a constant. Why don't we go ahead and just pull it out? We'll get a 2 pi I. And then we get e to the I theta, e theta. Okay. Well, that's 0. Why is it 0? Fundamental theorem of calculus. And evaluate e to the I theta at 2 pi, subtract off e to the I theta and evaluate at 0. That's nothing. If you've taken complex analysis, you might recognize that this is 0 for a different reason. This function is entire, right? And so this loop over here is contractible, right? Let's see what it gets. Okay, that's Cauchy's integral theorem, not integral function. Okay. Good. Okay. So the reason why I thought I had a mistake here is because I made this comp that I integrate 1 I'm gonna get 2 pi I, so you should think about this as an average. No. If phi is 1, then you get 2 pi. Okay, you still aren't holomorphic at, so you aren't defined at z the same. You have a pole there.
I think if you take like t to be mod z or something, you get 1, I think. But that's a different.
Okay, great. Okay, anyway. Great, so, oh wait, x star is 0, good. So that's what we've observed. Okay, by doing this integral. But here's the thing, we're never gonna get our hands on this in real life. Like right now we can do it because it's like the simplest situation ever. So we can explicitly write down this map. But in general, we're not going to be able to write down this map. But that's actually okay because we can still get this average. So what are we doing? We're integrating this function as we go around as many times as we need to until we get back up. And we can evaluate the function using analytic continuation. So another way to do this would be, okay, so I stop at some epsilon, I get square root of this. Okay. Now I do path tracking, go around, so, but I store the points at some intervals. Let's say 10 intervals or something. Okay, I recognize I'm not back where I started, so I have to keep doing this. And I go back up, still keeping track. And I use this discrete set of samples of the function to actually approximate my integral. This is a Riemann integral, right? I'm just taking the average value of these functions. And so we'll do that on Thursday on a computer. Okay. Near bad points, things lift up to look like punctured discs, parameterized by Helmholtz. Values at that puncture can be computed via values on the boundary of that disk. The boundary of that disk we can sample by going around in loops, thanks to homotopy continuation. And that sampling gives an approximation of the integral, because that's how we define integrals. We're going to look at it in the general setting. This was just the simplest setting, so that we could see really everything concretely. And we can actually write up these integrals, actually evaluate them. Again, in practice, we never get our hands on half of this. We're certainly never writing down solutions and radicals to these systems. So here's the kind of situation. So this is a homotopy where the target system, f of x, has 3 solutions. This one has multiplicity 2, because 2 paths are going to it. This has multiplicity 3, because 3 paths are going to it. And this has multiplicity 3 as well because 3 paths are going to it, but it's qualitatively different than the other multiplicity 3 situation. Here you want to imagine these 3 points kind of all coming together in some tangent way, which you can't draw over the real numbers, hence the dotted path. Here you have really something of order 2, and then something going through transverse. Okay, so we're going to see different behaviors. Okay. Since there are multiple roots at t equals 0 of this homotopy, this is one of our exceptional points. However, there may be others. So in the last case, there weren't other exceptional t numbers. That was one of the things we showed in our little exercise that we did last. Okay. But here there might. And of course, there might be some actually along the path, and that's part of why we have to use this gamma trick, blah, blah, blah. Okay. So there is some epsilon. Namely, you need something to be so small that the disk around t equals 0 does not contain any other exceptional points. Okay.
So when you mean exceptional points, these are the points where
Yeah. For us right now, it's solutions with multiplicity.
so finitely many.
Yes. Now we have some holomorphic B goes from 0. So in the coordinates, we'll call S, not the same S here, to X. Such that okay, so up here, say fix X star point of multiplicity on okay, such that E of 0 is X star. And pi opposed with P is S to the W for some W. Here, we can parameterize what X looks like near. Here we can as well. But one of those, so locally here, we have one punctured disk corresponding to this path. That looks like this. If you go around once, you really go around once. And then we have another, which has this twofold property. So let's call this C1, this C2, this will be C3, and then this will be 1, 2, 3. So you're getting all these punctured disks, right? Which have different numbers of going around. Okay, these are called winding numbers. But each one really is the image of a holomorphic map, the image of a disk under a holomorphic map. And so we can apply the Cauchy formula.
Some kind of polynomials, you mean, like z squares, the cube. The maps, phi.
B may not be.
Okay.
No. In general, yeah, so what do these look like near here, these paths? Generally, they look like isosceles. So there's some notes, which say a little bit about why that's the case. Before we have a t to the 1/2, negative t to the 1/2 for the branches, right?
Hmm.
But then as soon as we wrote s as being like t as being s squared, then these just look like s and negatives. I'm sorry, I just want to my boundary of b epsilon 0. I'll leave it to you, or you can look at the notes. You parameterize this boundary by theta goes to e to the I theta, and see a bunch of calculations, cancellations happen here. So that what you're really looking at is the average value as you go around. Okay. So this translates to an algorithm. You want to track these paths until you think you are so close to t equals 0 that you're closer than any other exceptional point. Okay, now in general, I haven't talked at all about how to even guess that, but just make t really, really small, have a heuristic. Okay, so that's a starting point. Then what do? Instead of continuing to go here, you stay at that distance. And you go around. And you see whether or not you came back to where you started. And if you haven't, you go around again. And if you haven't, you go around again. Every time you're going to go to some solution above this value. So eventually you're going to get back to where you started. Okay. And when that's happened, you take all the information you've learned along your path, because you've been keeping track of the values like every, length 0.1 or something, and you average them. And that's your answer. That gives you the approximation of the route you're going to. And that algorithm is called the quotient game, and we'll code this on Thursday. Okay, I think I am over time. I will stop the recording. I will take questions.